Okay. Well, you need to get up to speed on the app, or do you think you're good?
Which
This note taking now.
oh yeah.
It's not really any difference. I mean, right, text, and then the erasers here, and like just these two mainly. This should be all you
That's
need.
all I'm gonna
Yeah,
use.
I guess.
How much time should I aim to do it by 7? Finish by
Yeah,
7.
maybe a bit before if possible.
Okay.
Yeah,
I'll try to go too far.
sure.
I don't wish you last.
Yeah, and then just pause for questions a bunch.
Yeah.
Yeah. So yeah, I think we're gonna get started now. So just for your reference, this is gonna be recorded if you ever want to go back. And we're planning to also meet next week, and then probably gonna meet about 5 times total this quarter. The goal is to maybe build up to like Grover's algorithm and then really understand that and implement it in Qiskit. And then from there, like really get to run it on real quantum computers, maybe by like Google or IBM. And then that's like a nice project that you can maybe like put on your resume or something, right? So you can, I think it's a pretty cool thing. So we're just going to start today by like going over the basic formalism of quantum computing, and like how do you represent a qubit? What can you do to a qubit? Those are called gates. And then we're gonna go up to like doing simple like adding circuits, like add 2 bits together. And so Arv is gonna go through the slideshow, and then afterwards you guys will have like about an hour to work on the workshop that we have in QBraid. So yeah,
Hi everyone. Like Victor said, this lecture part is just going to be on the basics of like quantum mechanics. We'll go over like how you represent qubits and how you perform operations on qubits. And then after we'll be doing the project on QBraid. Um, okay, so the first part is just going to be going from classical bits to quantum bits, which we call qubits. So as you might know in classical computing, information is represented in bits, which have a definite value, 0 or 1, which you can read out at any time. So if you have some say you have some message, it'll just be some string of like zeros or ones like that, right? Um, in contrast, qubit in quantum computing is not exactly 0 or 1 at one, doesn't have to exactly be 0 or 1 at one time. It can be some what we say weighted combination of the two. And this is how we notate uh, the state of a qubit. So this notation is called a ket, where we have a vertical line and then some symbol inside, which this is the Greek letter psi, and then like an angled bracket to the right. And then this is what we said the weighted combination of 0 and 1 is. So this is the 0 state, this is the 1 state, and then we have some coefficients in front, alpha and beta, and those coefficients represent something that we're about to discuss. So yeah, that's the state of a qubit. And then and then after you're done with whatever quantum computation you decide to do, you're gonna perform a measurement on a state, and the formalism for how you measure is that you have some probability of measuring either a 0 or 1. So the important part is, while the state itself can be some combination of 0 or 1, the at the end when you actually perform a measurement, you'll get a classical outcome, which will just be 0 or 1 for sure. And and then we have probabilities to get either 0 or 1, and they're related to these coefficients. So as you can see, the coefficient from 0 is this alpha, and it turns out if you were to measure this state, the probability that you get a 0 is the what we is the it looks like the absolute value of this alpha squared, but in reality, these numbers can actually be complex numbers. So it actually is a little more than that, but I think we'll discuss that more in the workshop. But oops. Sorry. And then similarly, the probability you get a 1 is the coefficient in front of the 1, which is this beta, and then you square it. Should I go into that now? No. Okay. But yeah, you have the idea is in a state, you have these coefficients, and there's some probabilities to read classical outcomes from them. So that's the difference between like how we represent classical information, how we represent quantum information. Are there any questions on that?
this notation makes sense. Like I know it looks pretty weird, but again, it's just like saying there's a state 0, there's a state 1, and it has some coefficients. Same job.
Okay. And here's another thing, because these are probabilities, when we measure our state, we need to get some sort of outcome. So what we have this condition here where we say that the probability of getting zero plus, so remember this is the probability of getting zero, and then this is the probability of getting one. When you add those two up, you'll get one because you have to read either zero or one. So it's just a constraint on those coefficients. Does that make sense to everyone? Yeah. Okay, and here's the important thing. So while our state is in this superposition of 0 and 1, at the end when we perform this measurement and we redo the 0, 1, we collapse the state into whatever we read. So say we were to measure this state and we were to get a 0, the state post measurement would just be this 0 state right here. So let me write that out. Measure 0 and then state collapses to 0. So whatever you measure at the end, your state will collapse to whatever you measure. Does that make sense to everyone?
Well, the reasons behind why this is, like, if you're wondering that, we're not really gonna go into it. This is not meant to be a quantum mechanics course, so we're just gonna kind of like state some things and then try to explain them how you like work with them, but we're not gonna go too much into like the details of the plot.
Yeah, there's reasons for why this happens, but this is kind of just a high level. This is what happens without showing like the proof of why that happens. Everyone good so far? Okay, so these kets that we just said, 0 and 1, actually have, so that was called the ket form. They actually have equivalent matrix forms. So we basically have a matrix of two entries, and you can think of these like unit vectors, where ket 0 has 1 as its first entry, and then ket 1 has a 1 as its second entry. So pretty much, yeah, the first entry corresponds to 0, and the second entry corresponds to 1. Um, and we said that a general state is a superposition of the two. So if we want to convert that to like a vector form, then we can just convert the 0 into this vector form, and then a 1 into this vector form. And then when we multiply this alpha into this vector, you multiply each component of the vector by alpha. So then you get this alpha 0. And then with same thing with beta. And then you can add these two components. And then you'll notice that in this vector form of the state, the first number is the coefficient in front of the 0, and the second number is the coefficient in front of the 1. So it's just there are two different notations that are both helpful at certain times. So we'll kind of hopefully get you guys used to both. But yeah, does any questions on that? Okay. Here's an example question. Let's say we have this state right here, which is 1 over square root of 3 times 0, or ket 0 plus root 2 over 3 times ket 1. And we want to convert that to matrix form. Anyone want to tell me what that would look like? Yeah.
Sorry, the zero, state, right? Is the matrix form of that 0, 1 or 1, 0?
0 is 1 in the first entry. Yeah.
1 over 3, and the next condition would be square root of 2 over 3.
Yeah, exactly. So it's just the coefficients in front of 0 and 1. The coefficient of 0 is in the first entry, and the coefficient of 1 is in the second entry. Good. Okay. Now let's do a measurement example. So let's say you have this state, and like I mentioned, these coefficients can be complex. So, okay, well, the answer's already there. So I'll actually just walk through this one. So we want the probability of measuring 1 given this state. And like we said, it's something related to the square of the coefficient in front. Pretty much what we do is okay. So we said that so let's just say this is alpha 0 plus beta 1. We said that the probability of measuring 1 is this absolute value bar around beta squared. What this actually means is that we take beta and then what we say the complex conjugate, which is basically where you turn any I in the expression into a negative I, and then you multiply that by beta itself. So here in this example, beta star, you take 2 and then you turn the I into a negative I over root 5. And then beta itself is 2I over root 5. And then now we just have to multiply these two numbers. The 2 times 2 is a 4. There's a negative sign in front. I times I is I squared. And then root 5 times root 5 is 5. And if you recall, I is defined as the square root of -1. So that means I squared is -1, which means that this is 4 over 5. So the reason why we have this absolute value of beta squared is so that even though we can have complex numbers with our coefficients, when we eventually take a measurement, we're going to get a real number because there's no way of getting a complex probability. So does this calculation make sense to everyone?
Are people generally familiar with complex numbers? Maybe those people that want to go
Okay, let's move on. So oftentimes we won't just have,
something off. Okay, so one funny detail is that Seoul, like the organization that all clubs are under, has now decided to really charge clubs to use the projector, like $380 a quarter. And they canceled all funding for clubs to use. So I was hoping it wouldn't turn off, but we have another projector, so I'm gonna like spend a few minutes turning that on. But yeah, sorry. Okay.
concepts. Yeah.
Slides and before you even post it.
Yeah, well.
Well, this way.
Yeah, so we'll upload it to YouTube and then post it on Guidance Course. Maybe in the meantime, honestly, so let me some quick introductions, which I not to do. So let me just like name, major, year. I think we can just do that. So I'm Victor. I'm second year electrical engineering. Yeah.
I'm Arav, I'm computer science engineering. It's I guess my course is my third year.
I'm Adam. I'm a first year physics major. I'm Michael. I'm also the first year physics major.
I'm Eva, the second year physics major.
I'm Sunil. I'm a second year materials engineering major. I'm a DTI. I'm the first year on the bench.
I'm Francis, I'm the second year astrophysics.
I'm actually down on third year physics major.
No CS. Wow.
Maybe use my laptop.
Yeah. Close.
Yes.
Yeah. Yes.
Should we do an exercise? All right. Um, Right. Is this a valid quantum state? One.
Because this wears a pose and you don't add up to it.
Yeah, exactly. So 1/3 squared is 1/9. 2/3 squared is 4/9. Which is 5/9. What is the difference reason? If I add square roots down here, is that valid? Yeah. That-
Yeah.
Yeah, okay, yeah, it is valid. Because 1/√3 squared and 1/3. Oh, wait, no, it's not. I think, wow. Right, yeah. Okay, now is that valid? Yeah. 2/3, √2/3 squared is 2/3. And then it's 1. Yeah. And then. Okay, so for this state, what's the probability of measuring 0? Well, yeah, my vote is 3. And then. What if I added a y?
Well,
Oh,
still one.
yeah, still, but if I'm getting y. I'll just go through it. The complex conjugate of this is just adding a negative sign of one. And then the coefficient so. So you get negative I squared over 3. This one.
Okay. So, yeah, sorry to interrupt, but why it's some uglier than before. Hopefully, it'll be well. I think you just a focus bit.
I have a question for the complex.
Yeah.
How come, why don't you just square that on, like, little? Oh,
Because if you didn't add this, if you just had, then you would not have this negative sign, and then you get negative 1/3.
Okay.
Then the probably would be just not good. And there's also other forms of exponentials you can have. Sometimes it's using like e to the I theta or something. And in this case, what that would do is you would turn that I into a negative I. And then e to the negative I theta times e to the I theta is just 1. So it's just a different form of the exponential. Okay, so we just discussed how
Where should I turn lights off?
If you turn it from size up, it might be.
We try.
it's all or nothing, yeah.
Reasonable for you guys in the middle.
Okay, everyone can see? Fine, okay. Okay, so we just discussed how to like represent states and probabilities of one qubit. Now we're gonna go into how we do it for multiple qubits, because you're not gonna have one qubit. Like it's hard. You can't do much with one qubit. So here's our mathematical formalism of how we do multiple qubits. So we use this thing called the tensor product. So let's say we have two qubits with two distinct states. So the first qubit is in uh, state psi, so the Greek letter psi. And then we have a second qubit, which is in the state phi. This is the Greek letter phi. And the tensor product um, is just this circle with a times sign in the middle. And this is how we represent the joint state of the two by just combining them as a product. And then shorthand that we'll use a lot is that you could just omit the tensor product in the middle. And then sometimes we'll even just omit the like two separate kets, and we'll just put the two symbols in the same ket. Those are just shorthands, but implicitly they mean the tensor product. Does that make sense to everyone? So let's see what this tensor product actually is.
I think I'm gonna just try chocolate because I think it is quite faint. If that's okay with you all. We can see if it looks okay after it turned out. Or if it's too dark. So, I mean, much sharper, but now you guys can really see each other. Is that okay?
Yeah.
Okay, so here's that last slide, but the tensor product, we have two separate states. And then these are just the shorthands that we're going to be using a lot. So yeah, either omit the tensor product or just combine the kets. Here's how we mathematically do the tensor product. So let's say we have two general quantum states, some arbitrary combination of alpha and beta, or of 0 and 1 on both of them. And then here's their equivalent matrix forms that we talked about before. How can we mathematically describe this state, this joint state? So first we're going to do it in the bracket notation that we said before. So we just take psi tensor phi, and then here's their expressions: alpha 0 plus beta 1, gamma 0 plus delta 1. And then you can just distribute them like you would distribute like a regular product multiplication. So the first term goes to with this one, and then you get this, and then this term goes with the last, and then you get this, and then beta 1 goes with gamma 0, and you get this, and then beta 1 goes with delta 1, and you get this. Make sense, everyone? And then now we're going to use our shorthands from before. Oh, actually, first we're gonna. Okay, so first the coefficients will slide through because the tensor product and the regular product will commute. And then, so you can take these coefficients as alpha, gamma, just throw it in front, and then you get 0 tensor 0 in the middle. And then same thing for all these. The alpha and delta get combined, and then the beta, gamma, beta, delta. And then next, we're going to use our shorthand by saying that, for example, 0 tensor 0 is just 0, 0. It's just a way cleaner way of looking at it, because then it compresses into this nice form. Does that make sense to everyone? And now you'll see that there's four terms because we have two qubits. So when we had one qubit, we could either, so one qubit, we could either have ket 0 or ket 1. With two qubits, we can have four different states where we have two zeros, 0 and 1, 1 and 0, or 1 and 1. So it's basically like you're just counting up in binary in there. Does that make sense to everyone?
And then for n qubits, how many states do
Yeah.
you think you have? N squared?
Close.
Not quite.
Oh, two M, two
Yeah,
two.
2 to the n.
So it's really good. Right? Because those with each qubit you add.
Does everyone get that? So like if I had three qubits, I would have zeros. I'm not gonna write, actually I will write it all out. I'm not gonna write the cats, but if you had three qubits, you would have 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 0, or 1, 0, 1, 1, 1, 0, and 1, 1, 1. Wait, I missed one. What did I miss? Huh? Oh, that's 8, sorry. Yeah, so this is 8, which is 2 to the 3. Good. Does that make sense, everyone?
So one reason why this is kind of cool is you can imagine that like quantum computer with only n qubits, it's kind of naturally manipulating this very long vector, right? So it has some sort of like, I don't know, power that you can maybe almost already start to imagine that classical computers might not have.
Okay, so that's the Bra-Ket notation. Now we're going to use matrix notation, and the tensor product actually looks way easier. This is just how it's mathematically defined. So you basically take the second vector and then just like throw it into the first coefficient. So we get alpha times the second vector, and then the second entry will be beta times this. And then we get this length 4 vector. Alpha gamma is the first term from these two, and then alpha delta is the second term from those two, etc. And you can see that perfectly matches the form up here, alpha gamma, like this form. If you just were to stack the zero zeros, and the 0 0 term is right here, the 0 1 term is here, and then you just basically count down in binary and have each factor. Does that make sense to everyone? Okay. Here's another example. So here's a 2-qubit state. That's the expression. We want to write it in matrix form. Does anyone want to tell me what it'll look like? Yeah.
Top position will be 2 over 15. And the second will be, would just be 0.
Mm-hmm.
Over 15 and then over 2 over.
Yeah. Yeah, perfect. You basically just stack each entry on top, but the important thing is that there's no 0 1 term here, which means that the second entry is 0. Does that make sense to everyone? You ran a different color. Okay. Here's an example of how measurement works with a 2-qubit system, because you can imagine if you were to have 2 qubits, you're not required to measure both of them at the same time. You could just measure one and leave the other one alone. And if you measure a single qubit state, the state will collapse. But if you measure only 1 qubit of a 2-qubit state, we're interested in what happens there. So here's a general 2-qubit state where we just have those 4 terms, and then we have coefficients alpha, beta, gamma, delta. And suppose we measure only the first qubit. The probability of getting 0 is actually now the sum of the two kets, which have 0 as the first term. So in this case, 0 0 has a 0 in the first entry, and then ket 0 1 has a 0 in the first entry. And so that means the probability of getting 0 on the first qubit is the sum of those conjugates squared that we discussed before. So it's very similar, except you have to consider all the terms that have the state that you want. Does that make sense to everyone? And then similarly, the probability of getting 1 will be gamma mod gamma squared plus mod delta squared. Okay, and then similarly, we're gonna have the same constraint that this is the probability to get 0 plus the probability to get 1 has to equal 1. And yeah, does that make sense to everyone? Before we continue, I just want to ask, let's say we were measuring the second qubit instead of the first. What would the probability be of getting 1? So P1. What would that be? Yeah.
Would be beta squared plus, is that gamma, the last one?
No, the last one's delta. Yeah. Yeah. I mean, you had the right idea. So this term has a 1 in the second entry, and this one has a 1 in the second entry. So the probability of getting 1 on the second qubit is mod beta squared plus mod delta squared. Good. Okay. Okay, so now we know the probabilities of measuring specific outcomes. Now we want to know what the state will be. So let's say you measured let's go back to, let's say you measured on the first qubit, and let's say you measured a 1 on the second qubit. Then the resultant state will be something proportional to the two terms where 1 is the first entry. So because we measured a 1 on the first qubit, we know with certainty that 100% certainty that the first qubit is in the 1 state, but we don't know anything about the second qubit. But we don't know anything about the second qubit because we haven't measured it yet. So we're actually still in this superposition, but we're in like kind of less of a superposition as last time because we only have two terms now than one. But you'll notice that both of the terms will have a 1 in front because we measured a 1. And then this factor in front is what we call renormalization term, and basically what it enforces is that the sum of the probabilities still adds up to 1 after we measure, because that condition always has to be true. Does that make sense to everyone?
Can you just explain why, like, for the 0 and 1 states, we only look at the first entry in the, like, the broadcast notation?
Yeah.
Understand my question?
Okay, so like when we measured the first qubit, we know we got a 1, right? So that means this first, basically in each term we're gonna have, like in each term, let's just say it's like ket AB, right? This first term corresponds to the first qubit, and then the second term corresponds to the second qubit.
Okay.
So when we say that we measure 1, we want the terms where the first qubit is 1. Does that make sense? Yeah. Any other questions? Okay. Yeah, and this is just enforcing the fact that although we measured the first qubit to be in 1, the second qubit, we don't know anything about it yet. It could still be in 0 or 1. So if you're noticing here, you could still get 0 or 1 when you take that measurement. Okay, here's another example. Here's another 2-qubit state. And what's the probability of measuring 0 on the second qubit? Anyone want to try?
Would it be 2 over 5 squared plus 11 over 25?
Yeah, that's squared. Yeah, so these are our terms of interest because the second entry in the ket is a 0. So we're going to take mod 2 over 5 squared plus mod 11 over 5 squared, which is 4 over 25 plus 11 over 25, which is 15 over 25, which you can simplify to what? 3 over 5. Does that make sense to everyone? Questions? Okay. Now, if you measured, now given the same state, ignore, not like if you were to renormalize the state after the first measurement. If you were to measure 0 on the second qubit, what would the resultant state be? Don't worry about the factors in front. Just tell me like what 2 kets would we retain?
Same question. You got the first and the third one?
The first, third one. Yeah, exactly. So let's just say the coefficients are like A, capital A, and then we'll have 0, 0 plus some other coefficient, 1, 0. And the reason is because the second entry in the ket is 0, and we measured a 0 on the second qubit, so we know the second qubit's in 0. Does that make sense to everyone? Good. Okay, and then here's the exact answer, just with those coefficients. Yeah. Okay, now here's another interesting quantum concept called entanglement. So I'm just gonna give you an example, and then you can describe how it works. So here's a valid 2-qubit state. It's normalized and everything, but it only has the terms 0, 0 and 1, 1. And say you perform a measurement on the first qubit, sorry. What would well, it just said it. What would the state be if you were to measure 1 on the first qubit afterwards?
It'd be 1-1.
Uh, oh, well, there's probabilities of getting one. So you're not gonna have a definite one. So what better question would have been, just say, let's say you measure one or measure zero, and let's say you measure one. So if you were to measure zero, then what would the say be?
1/2.
1/2 what?
1/2. Or
No, not probabilities, the state itself. The probability is indeed to measure 0 and 1 or both 1/2, but I'm interested in what the state is after you make that measurement. So remember, we have to keep the kets that have 1 or 0 in the first qubit. So for 0, which kets have 0 in the first entry?
First one.
Yeah, the first one. So remember, so we're going to be in state 0, 0 after we make the measurement, and there's nothing else because we don't have a 0, 1 term. So because there's no 0, 1 term, all we have is a 0, 0 term, and actually there's no coefficient in front of it. The coefficient is trivially 1 because there's a 100% probability associated with it. Does that make sense, everyone? And if you were to measure 1, 1, you would be in 1, 1. Does that make sense? Any questions on that? Okay, and then this is just saying that if you were to measure a 0, the state would collapse to 0, 0. But the interesting thing here is now that the second qubit is now definitely a 0 because there's no 0, 1 term. But we haven't measured the second qubit, yet we've collapsed its state to 0. And similarly, if we measure a 1, then the state becomes 1, 1. But the second qubit is now 1, but we haven't actually measured it. So what's going on here? This is pretty much what entanglement is. So the measurement of the first qubit somehow allowed us to determine what the first and second qubit are. So if we were to measure a 0 on the first qubit, we know that the second qubit's also in 0, and vice versa. Yeah.
So then why in this 2-qubit system is there no like 4 states? Like why is there no 0, 1 and 1, 0? Yeah.
So you're not required to have those. So in general, you could have a 0, 1 and 0. Yeah, exactly. So in this state, the probability of measuring 0 on the first qubit and 1 on the second qubit is 0, and the probability of measuring 1, 0 is also 0. So there's just no terms of that. Yeah.
Does this like entanglement only apply if they both have like 50% probability?
No, you could have something like 1 over, like doing the same thing we usually do, like this, and then this is also a valid quantum state because it's normalized. That's all we require, that the sum of the probabilities equals 1. So it would just be a different probability because in this case, the probability of measuring 0 on the first qubit is 1/2. But in this case, the probability of 0 on the first qubit is 1/3. But it doesn't have to be 1/2. Any other questions?
Should go slightly faster.
Okay, yeah. Oh, we have some case. Okay, these are entangled states. Yeah. Does that entanglement good? Okay. Just a quick question again. If you were to measure 1 on the second qubit of this state, what could you say about the first qubit?
So it's gonna be 1.
Yeah, exactly. Because there's no 0, 1 term, which means that the only term with a 1 in the second entry is this 1, 1. So when we measure 1 on the second qubit, we know the first qubit's in 1. Make sense? Okay. Okay, now we move on to how to actually do operations on quantum states. So we discussed how to represent single qubit states and how to represent multi-qubit states. Now we want to perform computation on these states. So the way we do that is with quantum gates, and these are operations that we apply to states, and we get a new state as an output. And no matter what gates you apply to a circuit, like we said, the sum of the probabilities of getting 0 and 1 have to add up to 1. So they always have to be normalized afterwards. And another idea is that gates can act on multiple qubits. So we call those multi-qubit gates. And one of the important ideas of quantum mechanics is that it's linear. So a gate will be linear. So let's say we have a gate U and we were to apply it on this superposition state. We can distribute it past these coefficients and get alpha U on 0 plus beta times U on 1. So it's basically just distributing it through. And the consequence of this is that we only need to know an action, a gate's action on 0 and 1, because this right here is a general quantum state. Does that make sense to everyone? The linearity property? That'll be important. Okay. Yeah. And similarly, we showed a representation of qubit states as a vector. So in this case, our quantum gates can be represented as matrices, and then we can basically multiply a matrix and a vector, and then get a new vector, like a transformation. And you don't have to be too proficient with doing matrix multiplication because we'll show it all out, but we'll show that interpretation as well. And here's just some figures of how classical and quantum gates differ. So in a classical gate, you have some computations like doing ands and ors and whatnot. And then in quantum gates, you have these lines that represent qubits, and then we apply some gates on them. But now let's discuss the actual gates that we're doing. Any questions before that? Okay, so here are the basic single qubit gates. So these gates will only act on one qubit. The first one is an X gate, which will flip the 0 state and the 1 state. So, and here's its matrix representation. So like we said, these gates can be thought of as matrices. And here's a diagram to show what it does. So this is a circuit diagram. So let's say we start in the 0 state, and then we apply this X gate, and then we end up in the 1 state because we flipped it, and vice versa. If we start in the 1 state, we apply the gate, then we'll end up in the 0 state. And here's the formalism in matrices and vectors. So if we start in the 0 state and we apply this matrix that represents the X gate, if you know how to do matrix multiplication, you'll actually get the matrix representation or the vector representation of the 1 state. Does that make sense to everyone? Any questions? Okay. And here is an example of the linearity property. So let's say you were to apply the X gate on the most general quantum state, which is this alpha 0 plus beta 1. You can distribute the X through, and then you get alpha, and then X applied on 0 plus beta times X applied on 1. We know what X does on 0 and 1. We just said that up here. And X on 0 will flip it to 1, and X on 1 will flip it to 0. So we just change the 0 and 1s in the kets. Does that make sense, everyone? Okay. Here's the Z gate, which will do nothing to the 0 state, but will multiply the 1 state by -1. So the coefficient in front will just be multiplied by -1. And here's the matrix representation of it. And here's the same circuit diagrams. So if you start in the 0 state, you apply the Z gate, you'll end in the 0 state, and that can be computed out by the matrix representation. If you start in the 1 state, you'll end up in -1, and that can be seen in that matrix calculation as well. Does that gate make sense to everyone? And then we have the same linearity here, where if you were to apply Z on the most general state, you can distribute it through. Z on 0 does nothing. But then Z on 1 will add this -1. Oh, shoot. And then Z on 1 will add this negative sign right there. Does that make sense?
So how to read the quantum circuit diagram, which is like
Oh, yeah.
cat one, the line, the box, and the Z, and the 0.
So it's like time goes from like left to right. So this is your initial state. And then you go forward in time, you apply the Z gate, and then this is your final state. Is that good with everyone? Okay. And this is one of the interesting gates called the Hadamard gate. And this is what generates our superposition. So the X and Z gate will just do some weird interplay with just 0 and 1. Now we want to actually generate the superposition states we were talking about before. So what the Hadamard gate will do is that it'll change the zero state into this, what we call equal superposition of 0 and 1. And then it'll change 1 also to this equal superposition, but with a 1, with a negative sign in the middle. Here's its matrix representation, just 1 over root 2s with some minus signs. And here's the same circuit diagram. So again, time left to right. If you start in the 0 state, you'll end up in this equal superposition state. And here's the matrix math on it by just multiplying the Hadamard matrix times the 0 vector. Is that clear with everyone? And you get this vector sum, which you can collapse into like 1 over root 2, 1, 1. Yeah. It has to do with changing 1 into with that negative in front, and that's where this term comes from. Any other questions? Okay, feel free to stop if there's more questions. Yeah, and then you can show the same thing with 1 going to this equal superposition with the 1 or with the minus sign in the middle. Here's an example. So let's say you have a 1 state and you were to apply H, the Hadamard, and then you were to apply Z, and then you were to apply X. I think I work out this example. Okay, no, I don't. Does anyone want to try it? Like maybe someone can do like the Hadamard first, and then someone else can do the Z, and then someone else can do the X. So let's say you have a 1 state, and then you apply H. Does anyone remember what we get?
The minus superposition states.
Yeah, exactly. So it'll be 1 over root 2, and then 0 minus 1. Good. So this right here is the state at this point in time, right after the Hadamard gate. Now let's get the state at this point in time by applying Z on this state. And remember that the gate is linear, which means that the Z can be distributed into the 0 and the 1 separately. So does anyone want to tell me what we would get after applying that? Do you remember what Z does?
Let's make it +1.
Yeah, exactly. So it'll leave 0 unchanged, and then it'll change the -1 into a +1. So this, again, is the state at this point in time. Now we want the final state, so all we have to do is apply X to this gate. And what do we get? By the same linearity thing. Do you remember what X does?
You get the same thing, no?
Yeah, you'll get the same thing. If you want to do it directly, you would flip the 0 to a 1 like that, but that's equivalent to just 0 plus 1 because it's addition. And that is the final state after the circuit, which is the answer there. So does that make sense to everyone? Any questions on that? Okay. Now we'll move on to the 2-qubit gates, which act on 2 qubits at the same time. So here is the main 2-qubit gate that we focus on, called a controlled gate. And what it'll do is, so you have two, what we say, registers, which are qubit states, X and Y. And what it'll do is, X is called the control. This right here designates the control. And then this right here designates the target. So the black dot. And what the 2-qubit gate will do is it'll apply the gate U, the single qubit gate U, to the target qubit if the control qubit is in the 1 state. So it's like a conditional. It's like if the control is 1, so if I'll just call the control C, if like the control is 1, then apply U on the target T. So just as like a little thing. Does that make sense, everyone? And the gate that we'll see a lot of times is the C naught, which is the controlled X operation, which looks like this, where the black dot again is the control, and then this is the target, and then that big hollow circle, like with a plus in the middle, is like a interesting way to represent an X gate, but I don't really know why the convention's like that. But here are the four different operations of a C naught. So let's say the input states are 0, 0. After we apply the C naught, because the control qubit's at 0, it's going to do nothing to the target qubit, so you end in 0, 0. Similarly, if you start in 0, 1, since the control is in 0, you do nothing to the target and you end up in the same thing. And then if you have 1, 0, the control qubit's in 1, so then you have 1, 1 at the end because you flip this because the control is in 1. And then finally, if you start in 1, 1, you'll end in 1, 0 because the control is in 1. And then here's a table just representing those outputs.
And the top right is again the control qubit state.
Which one?
The top right
Top right?
in the diagram. So it's the control.
Oh, yes, this, like this right here.
No, like the state next to it. Like
Oh, yes, this is the controls, like the state of the
and on
control.
right, it again.
Oh, yeah, that's the control, that's the state of the control qubit after the C naught.
Is it always the same as?
Yeah, that doesn't change. Yeah. Well, it will change if it's in superposition, but in this case, it's just 0 or 1. Yeah. Okay, here's an example using C naughts. We want to know the fun. Should I go through this? Okay. So here's an example of here's a circuit example with 2 qubits this time. And again, we want to know the final state. So does anyone want to? So I'll just set it up by saying that we start in 1, 0, and then we apply an H on the first qubit. So remember, if you recall, we start in ket 1, 0, and then we apply H on the first qubit. So this 1, 0 is the state at the beginning, H on 1 times 0. Does anyone remember what H on 1 is?
The superposition.
Yeah, with the minus sign. So it's 1 over root 2, 0 plus 1, and then tensor 0. Oh, the minus sign that I just said. And notice nothing happened to the second qubit because there's no gate in the diagram there. So that is the state right here, after here. And remember, it's a 2 qubit state, so it's the state of both qubits. We use the tensor product to represent the state of those 2 qubits. Now, here's the interesting one, and I'll make it easier by simplifying it a little. When we apply the C naught, so this state right here, I'm going to simplify it by bringing this product, or by bringing this 0 kind of like into here. And remember, we use our shorthand where we're with a tensor product, we just combine the two things in the ket. So then we get 1, 0 like that. Does that simplification make sense? Where we just kind of throw the distribute the tensor product into the parentheses and then combine them according to the shorthand. Okay, and the reason why I did that is to make the C naught a little easier. So if I were to apply C naught onto this state, 1 over root 2, 0, 0 minus 1, 0. What would that get? And remember, the linearity still upholds, meaning that the C naught can go here, C naught can go here. So if you remember the table from the last slide, it should be easier.
It would be 0, 0 minus 1.
Yeah, exactly. So 1 over root 2. For the first term, because the control qubit is in 0, the control qubit's the first qubit here. So because the control is in 0, we do nothing to the target, and we just get the same thing. For the second term, we get the control qubits in 1, which means that we flip the second qubit like that to a 1. So that is the state right here, which is the final state. Does that calculation make sense, everyone? And then that should be, oh, it worked. All right, well, I worked it out, but I forgot about it. But you guys got it right. Here I started with the shorthand of just saying it's 1, 0, and then apply H, and then simplify it a little, and then do the C naught. And then this is exactly what we said. So if this is our final state, if you remember our discussion of the multi-qubit states, does anyone notice something about that state? Which I mentioned was one of the weird things about quantum mechanics. If you recall, measurement and stuff like that. Yeah, it's entangled. And the reason is almost exactly like the example I gave before, that a measurement of the first qubit will determine the second qubit because there's no like terms, there's only two terms that are directly correlated with each other. Does that make sense? So if you were to measure 0 here, the second qubit would be in 0. If you were to measure 1 on the first qubit, the second qubit would be in 1. So it turns out that this circuit here took an unentangled state, 1, 0, right here, and then created an entangled state after. Does that make sense, everyone? Okay, and then I'm pretty sure I talk about that here. Yeah. The C naught can be used to create entanglement because of that conditional, like if the first qubit is 1, if the control qubit's 1, then do something to the target. So that's intuitively what created the entanglement. Okay, and then the final thing we'll talk about is just if you have multiple controls. So we said that a C naught has one control. There's another gate called the CC naught. It's also called a Toffoli gate, which will have two control qubits, which we denote C1 and C2, and then also a single target qubit. And the operation is very similar. But this time it's based on both the controls. So if both the controls are in 1, then it'll apply the naught onto the target. And if even one of them is a 0, then it won't do anything. So if you can see this table, in these first 6 cases, at least one of the controls is in 0. So it does nothing. So it does nothing to the target. But in these last 2 cases, both the controls are in 1. So it'll basically just flip the target. Does that make sense? So it's just a multi-controlled gate. And then you can keep going. You can do C, triple C naught, or whatever. And I think that's the last part. Here, do we need to go over this?
So I guess we can quickly
Okay.
jump to the next thing. So this now we're pretty much done with all the contents for today. So we're gonna jump over to Cupid, and you guys will like work on which we're on. So I'm just gonna reorder through them. So this is what it'll look like after I add you to it. Maybe to quickly show you what's in your end. I think when you go to account.cubase.com and we'll put this in front of the Discord, you will see like all these tabs on the top. You go to courses, and I think you should probably only see like the bottom two here. You can launch the ebook, and then it'll navigate you exactly to this page. So basically here, we're going to use the KISS algorithm from IBM, which is a very popular way of reaching backends and also using quantum state simulators. So we'll use that to like basically some of the computations we're going to do in this notebook. So you can basically run these cells by quick memo. Yeah, something like that. And then basically we're just like embedding some of the relevant info. We're also going to put the size of the Discord, and then there we can edit the code as well. So you can see you can select it and just edit it like a normal code editor, and then when you're done, you can run it. And of course, here there's going to be syntax error. So this is in Python. If you're not familiar with Python, we can slide this down and give you some quick like pointers on how to start. But the code is all like pretty intuitive, and the only things you need to change are marked as like to do. And we're trying to give you all the syntax that you need. So you really don't need to know too much about CS or Python. So then we have like questions embedded throughout that you can try. So there's a submit button over here. And so on. And then, yeah, so just more examples, more questions. And by the bottom, you're gonna try to implement some of these class gates, exclusive or and. So if you don't know what these gates are, again, you can like and explain them more depth to you. You can Google it wherever you want. And so in these, you can see that we make it so that like bottom is like texting code. So it'll like test your implementation, and the top is some implementation in the quantum segment about this gate. So there's just this like guideline of you only need to add one line here and then it should work. And then for and it's a bit more complicated. We removed some more of the skeleton, I gave you some more hints. So you have 8 lines in here, and then for this like, half adder, which we can talk more about, you get here, it's like about 10 lines. It's all very similar to what we came about. And so that's all we have. So you guys, I guess I forgot to say that you'll need your laptops, but you have a laptop and you can look it up if you're ready to start it. That's what's in the picture.
Sorry, can I see? The slide.